Yeah, Bismillahirrahmanirrahim. We start our lecture today. We continue for the sequences. Okay, in mathematics, a sequence is a numerical enumerated collection of objects in which repetition are allowed and order matters. Okay, this one is enumerated collection. Basically, sequences are enumerated sequences. Okay, like I said, it contain members lah. It also contain members. Same goes to a set. Uh, the number of element is called the length of the sequence. Okay, we have a sequence, and then we have the length. Okay. Okay. For example, we have a sequence -2, 4, -8, 16, and -32. The set corresponding to the above sequences is -2, 4, -8, 16, and -32 lah. Okay, example. Okay, we have a sequence. Example, we have a sequence. Okay, -2, 4, -8, 16, and -32. Okay, for the set, okay, you have -2, 4, -8, 16, and -32. This one for the set. Okay. And then another example, you have a sequence 1, 0. Here for the set is equal to the members. It's 0, 1, and 0. Okay. The set is corresponding is 0 and 1. Okay, we have a sequence. Okay, this one is for the recap. Recap for the functions we have learned, and we also discussed about the function from set A implies to set B. An assignment of exactly one element uh, of B to each element of A. Okay, one element. Okay, we map. Okay, we map one element of B to each element of A, and A is the domain of the function, and B is codomain, image and re-image of the domain. And then we have one-to-one function, okay, one-to-one function, and then we have onto surjective function, and bijection can be inverse. We also look into the bijection, okay, and then we must fulfill all the bijection requirements, one-to-one function and onto functions. And then we also look at the flow and also ceiling. Okay, this one is for the composition. Okay, composition also we denote by the F. Okay, sorry, by the F. Okay, G. Okay, then this one is floor less than or equal to X. And then we have a ceiling greater or equal to X. Okay, this one for the sequences. Sequences are represented on the list, like I explained before. Sequence is defined as a function from a subset of n natural number to a subset, a set of s. Okay, we use the notation an to denote the image of the integer n. We can call as an as a term of sequences. Okay, a subset of n. And we have 1, 2, 3, 4, 5 until n. This one is sequences. Okay, and then for the set, we map for the set as set 1 and set 2. Okay, we have A1, A2, A3, A4, A5, and AN to AN. This one is a term. Okay, we have N1 mapped to A1, okay, is equal to 2, okay, and then we have 2, N equal to 2, okay, for until AN is equal to 2N, okay, multiply by 2 lah. Okay, in other words, this one is multiplied by 2, AN terms. Okay, and then we use the notation or AN to describe a sequence. That important, do not confuse with the element bracket that used in the set notation. Okay, it's convenient to describe a sequence with a formula. For example, the sequence of previous slide can be specified as set of AN, whereby the AN is equal to 2N. Key sequence also use the same notation as I said, list each element and separated by commas, and then put a curly bracket around the whole things. Sometime in the sequence, we call it as a curly bracket. Sometimes we call it as a set bracket or braces. Okay, this one is ordered list that we see. AN equal to 2N is the ordered list. Okay. Okay, do you have any question? Is it okay? Okay, tak apa, Syasha. Line problem eh. Okay, nanti kalau tertinggal tengok kat ini kat YouTube eh. Sequence, what sequence is basically is the uh, object eh. They do not have a unique like connection to any other. So you have done so far. Okay, is a set. Eh. Okay, you have also seen a set. Eh. Okay, and then okay, then we have a formula. Formula. We have a series of a formula. As you can see, is you can formulate from the sequences. Okay, you this one is more on you find a pattern. Pattern. For example, you have an is equal to 2n minus 1. K is a1 from sequence a1, a2, a3, a4, a5. We have a formula, okay, and then we have an equal to negative 1 power of n, okay, a series of a1, a2, a3, and so on. This one here. Okay, and then we have an equal to n power of 2 plus 1. Okay, we have 1 power of 2 plus 1 is equal to 2. 2 power of 2 plus 1 is equal to 5. A33 power of 2, 9 plus 1 is equal to 10, and so on. KAN is 0.25 and so on. Okay, this one is a pattern. What are the formula that describe the following sequences for A1, A2, A3, and so on? Okay, we can describe sequence in order, like you said, or we can use the notation. Okay, same as the notation of a set. Okay, separated by commas. And then we also can define a sequence as a rule. The sequence usually has a rule which is okay, which is jump start at 3 and jump 2 every time. For example, this one as a rule, we can see like this. Okay, this one we define sequence as a rule. Okay, from 0, 1. Okay, this one we jump. This one we jump 7. This one we jump 9. Okay, this one plus 2, plus 2, plus 2. Okay, for this example, the sequence of we have 3, 5, 7, 9 start at 3 and jump 2 every time. Okay, and then we seen before as a formula. Formula. For example, we have n term, which whereby the n could be any term of number that we want. Okay, the formula. For example, we have n term. This one as the formula. Okay, for the formula. Okay, like we see an. Okay, for example, we have test rule. For example, we have test rule 2n. Okay, and then we have n, and then we have term. And then we have test rule. Here we have ny. Term is 3. Okay, and then test rule is 2n equal to 2 multiplied by 1 is equal to 2. And then we have 2. The term is 5. Okay, and then 2n equal to 2 is equal to 4. And then we have n 3. The term is 7. Okay, and then 2n is equal to 2 multiplied by 3 is equal to 6. Syasha okey ke? Boleh ke Syasha? Okay, this one is based on rule and based on the formula. Okay, and then we can make a sequence as a notation. Notation. For notation. For example, we have x n, whereby the x is the term and n is the term number. Okay, so the rule that we see, okay, for example, we have 3, 5, 7, 9, 11, and is we can describe and written as Sn equal to 2n plus 1. Okay, how to calculate the x10 is equal to 2n plus 1 is equal to 2 multiplied by 10 plus 1 equal to this one 20 plus 1 is equal to 21. Okay, okay, 3, 5, 7, we have 13, 15, 17, 19, 21. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this one is the term and then term number lah. Okay, for the notation we have term and term number. Okay, this one. Okay, for the n, okay, natural number, and then we have set 1, 2, 3, 7, an, and then we have an equal to n equal to 1, a1, n equal to 2, a2, and so on. So we can conclude this one as an is equal to 2n minus 1. Okay. And then we have string. Finite, finite mean that you can count. Finite string, finite sequences are also called string, denoted by a1, a2, a3, and so or to an. The length of a string is the number of the term that consists of it, and the empty string contain no element, no terms at all. It has a length of 0. Okay, we have string. Okay, before this we have learned sequences. A string is an ordered sequence of elements which are symbol or letter or an alphabet, and represented by simple concatenation of this element. It basically is introduced by Michaelet in 1986. Okay. Okay, and then we have summation. Summation is the we have the upper limit, we have the terms, and then we have the lower limit, and then we have a summation. And T1 is represented by the multiplication. Okay, it represented the sum. And then the variable j is called the index of summation. A running form is the lower limit, whereby the m is the upper limit of n. We could as well have used any other letter to denote this index. Okay, for example, we have the summation of n, okay, ag, am, this lower limit, okay, plus m plus 1, am plus 2, and so on, whereby the n is the upper limit. Okay, and then we denoted for the, okay, upper limit is 6, okay, upper limit is 6, j is 2, okay, lower limit, and then we have a upper limit of 6, ag, 2, 3, 4, 5, 6, 8, 6. This one is summation. Okay, the idea of sigma notation is sigma notation. Okay, okay, another example I give to you. Okay, I give to you a simple example. Okay, we have case going 1 plus 2 plus 3 plus 4 plus 5. Okay, plus 9 plus 10. Okay, to find the sum of the first of 100 numbers is very difficult to find, because so that be 1 plus 2 plus 3 and so on okay, until we 99 so mathematician said, well, let's find some notation find notation instead of having a dot dot dot, you see sometimes done so we can clearly express this type of sum okay, and why where sigma notation come from so the sum up here, okay, should represented as a sigma. Okay, we can represent this one is equal to sigma. This is a Greek letter, a Greek letter, right, right there is on the left hand side. And what you do is you define the index. You find the index and start your index at some values. So let's say you index start at 1. Okay, I just use I for the index. Okay, okay, we have learned this one. I for the index is equal to 1. And I'm going to go to 10. Okay, 1. Okay, start from 1, and the upper limit is 10. Upper limit is 10. And it goes to 10. And I'm going to sum the i's. Okay, we want to sum the I. Okay, we want to sum the I. Okay, so how does this translate into the right over here? how we want to translate right here. Okay. Well, what you do is you start wherever the index, index, index is I equal to 1. If the index is set at 1, set I is equal to 1. Okay, write down the 1 and then the increment the index. So I will then be equal to 2 lah. Okay, I equal to 1. Okay, I equal to 1, and then we goes I plus 1 is equal to 2 lah. And you summing each of this term as you go lah, and you will go until the way I is equal to 10 lah. Okay, because we have defined the upper limit is 10 lah. So given that, I just you want to pause later on this video and write a sigma notation. Okay, for another exercise. Okay, we have a sigma notation here equal to 1 plus 2 plus 3 plus 4 plus 5 until 99 plus 100. Okay, Nadia. Okay, how about this? How you write this sigma? Nadia? No, Nadia? Okay, well, again, this one, I also start with 1 lah. Okay, with 1 again. Okay, I equal to 1, and then you are not going to stop until I is equal to 100 lah. Okay, so the upper limit will you set will be go for 100 here. Okay, and then we are going to sum up all of the i's. Okay, we want to sum up all of the I. We make this one I. Okay. Okay, let's do another example. So far, is it okay? Ain Safina, okay ke? Ada soalan? Ya, ya. I sama dengan 100. I, I sama dengan 1. I sama dengan 1 tu lah lower limit. Lower limit, we have upper limit, and then AJ stand for is this one is a summation, and TI is a multiplication. Okay, you have a lower limit increase. This one is increasing by the index. Okay, by the index of summation. For example, here if we have I equal to 1 is from the lower limit until 100 is the upper limit. I 100, and then what you want to do is you index. You want to sum all of the numbers from 1 until 100. Okay, we do another example. Okay, let's imagine the sum from I equal 0 to 50. Okay, we have here another example. We have I equal to 0. Okay, and then the upper limit is 50 lah, because we want, okay, I equal to 0, and the upper limit is 50 lah. Okay, let me say pi is square. Okay, we have formula pi of I square of 2, power of 2 lah. Pi is, how to draw the pi? Okay, okay, what will this sum look like? And once again, I encourage to see again my videos, and write it out and expand out this summation. Well, just go step by step. Okay, when I equal to 10, this will be the pi times 0 squared. Okay, and clearly 0 lah. I will write down the pi times 0 squared is equal to 0. Okay, pi. Okay, then we are increasing our I. We make sure that we haven't hit our boundary 50, okay, or the top value or the limit value. So now we say that I equal to 1 pi times 1 square root. So plus pi times 1 square is plus, okay, and then we plus the pi multiplied by 1 square root. Well, 1 is our top value right there, and then we are now keep going. Okay, okay, when we want to stop, Suryani, Suryani, Ikhwan, ada Ikhwan? Bila kita nak berhenti, Okay, until 50. Okay, we plus again pi. Okay, okay, we plus again and 2 power of 2. Okay, I think you see the pattern there. We're just going to keep going all the way. At some point, we are going to keep incrementing. Our I is going to 49 pi times 49 square by 2. Okay, we keep going until pi 49 square by 2. And finally, we increment the I equal become 50 lah. So we are going to plus pi times 50 squared by 2 lah. Okay, finally we have plus, okay, kecilkan sikit. Okay, plus pi 49 square root plus pi 50 square root. Okay, equal to this top boundary. So we can stop. Okay, because we have the boundaries, and so now you can see the notation. This sigma notation for this way, some was a much cleaner way. decimal notation for this sum was a much cleaner way, a much purer way of representing the sum, than having to write out the entire sum. Okay, so far, do you have any question? Is it okay? Chicken okay, girl? Okay. Then I think we should have a rest for 5 minutes. Later we continue.